Okay, solid state soft starters. They use phase control. Essentially, they use SCRs that switch the incoming AC and reduce the voltage, usually just during starting. Um, so by reducing voltage, we do lower the speed of the motor somewhat because we increase slip. Um, we way reduce the available torque for the motor because you've got less voltage, so less current, so weaker magnets. Um, so if you've already done the DC modules, then you've seen some phase control stuff. Um, so as we go through here, some of this might be a bit of a review. So we're going to go back and just take a look at phase control, how firing angle works, and we're going to mostly in this segment just focus on soft starters. We'll kind of skip over the DC applications because that was done in the DC modules. So we are using SCRs to change the incoming voltage. Don't get this confused with VFDs. So if you look down here, this being the incoming voltage, we can use an SCR here. So here's the SCR, here's the load. Power would go through the load, right? And then be sloshing back and forth like this, right? Back and forth, AC. Well, this diode only works in one direction, so that chops this chunk off. And then depending on when we fire, in other words, when we give a pulse to the gate, we can determine when this will turn on. So here we're firing midway, and that's our output voltage. So the voltage, the power that the load sees is much less than had the SCR just been shorted. If the SCR had been shorted, we'd see the whole waveform. Because it's one SCR and it has a firing here on the gate, we're just seeing this small amount of power get through. And so that would result in a dimmed light or a slower motor. But be clear, we are not changing AC, we're just changing voltage. So this is what it looks like with an anti-parallel connection, which just means we have an SCR pointing in both directions so that we can get the top part of that AC waveform and the bottom part. In that slide before, we just had one diode or one SCR, so we missed an entire half. And this is something called a triac, which basically integrates these two together. So what firing angle is, it's just the angle in the waveform when we fire, right? So if we start at 0, and this is 180, and this is 360, so if we fire at 90, we would get half of the voltage through. And assuming that we fire 90 here, then we could, we'd get half of it through. This thing, a conduction angle, isn't used very much, but it's just the opposite, right? We're conducting for 90, we fired at 90. So this was what, some various outputs could look like here. If we're firing early at a low firing angle, we get a lot of power out. We're firing midway, we get half, and we're firing late in the waveform, and we just get a little bit. So this is kind of representing these hash marks, how much power is getting through. All right, so this is a dim light, this is a bright light. This is a motor started with a really low voltage. This is a motor, that we're picking up voltage on. Just one more picture of the same thing, kind of. Now this is shown with it maybe in a rectifier bridge where we've now flipped over this bottom chunk, right? This is somewhat of a review from electronics class when we did this. So this is DC now. We've just put it through a bridge. Okay, this wouldn't really be too handy, half wave. But here we go. Here's a single phase rectifier where we'd be using SCRs to change the DC voltage. Now this would be the most common three-phase. This is how we run drag lines, right? Or maybe a shovel, big DC motors, and we'd have a bridge like this for one direction and a bridge like this for the other direction too. Now here we go in a soft starter application. We're going to reduce inrush current on an AC motor. We'll just ramp the voltage up during startup. We'll set up the soft starter for a ramp time. The power will go through the SCRs for a little while, and then once we're up to speed, we typically close a run contactor and just take the soft starter out of the picture. So here's the SCR shown anti-parallel, so we get both chunks of the wave, and you can see this would be in the beginning when you're just barely starting the motor, and as you cranked the firing angle, this is well, this is actually shown backwards. So here's the firing angle. This would all be on out here. But anyway, we just slowly ramp up the voltage. And there's some downsides to that. You don't have torque much. Won't have much torque. The cool thing about VFDs is a VFD, we're changing the frequency also, so we can we don't lose torque. We can have a low frequency and a low voltage, and that'll give us a low inrush, but we can maintain a nice full torque. But this is a cheaper, simpler application, soft starter. Okay. Now another application for synchronous, or I'm sorry, for phase control would be to supply power to the rotor of a synchronous motor. So that's what's shown down here. This would be the slip rings on a synchronous motor. This is basically an induction motor that's got some wound rotor out, windings that are wound in the rotor, and then you power those up and you create this fixed DC powered magnet in the rotor. But they're powered by phase control, essentially. So when we say DC excitation, it's basically a DC power support, or a power supply. And when we call them static exciters, we just mean there's no moving parts. They used to be exciters were DC generators, and now we use solid state. So when those first came out, they called them static exciters. These are exciters that aren't spinning, they're solid state. But they use that same phase control theory. Now, you can look and see here, this is excitation for a DC motor. In other words, the exciter here is powering the fields of this. This is a haul truck. So then when you hear that term excitation, we just mean kind of a DC source that's going to power up a winding. So it might be a field, a stator field on a DC motor, or it could be a excitation of the rotor on a synchronous motor or synchronous generator. Alrighty. So phase control has some limitations. One of the things about it is you got to start with AC, right? And also you can't exceed the input voltage. In other words, you can only ramp the voltage down. You can't raise it up. So pulse width modulation is kind of another approach. So you can't use phase control in a battery powered device is kind of the key here. So that's a little on phase control, and on the lab you're going to do a little soft starting with phase control.